Hi everybody. In our last lecture, that is in the lecture number 10, we had completed up to the 50 number question. Okay, this is a 50 number question, and in today's lecture, let's start from 51 number question. This is the 51 number question. So it is given that an one-dimensional box of length A has 3 electrons, and we have to find the lowest energy of the system. Okay, so how can you find? With the help of Pauli exclusion principle. Okay, so according to the Pauli exclusion principle, you configure and place the electron like this. How can you place? You place two electron in the n equal to 1 state, because one electron can be in the off spin, and the other electron can be in the down spin. Okay, so the n equal to 1 level can be accommodated by 2 electron. So another electron will go to the n equal to 2 level. Okay, and you apply that formula n square pi square h squared square by 2m s square. Okay, so with that application of that formula, after calculation you will get 6 pi square h squared square by 2m s square. But if you see the options, there is no option like this. So no doubt this was a grace mark question. Okay, that means irrespective of you have answered or not answered this question, full mark is given to all student. Okay, so now coming to the 52 number question, it is given to find the expectation value of R in the ground state of a hydrogen atom. Okay, where A naught is the Bohr radius. So how can you find? So to find the expectation value of the electron in the ground state, you need the ground state wave function for the hydrogen atom and the expectation formula. Okay, the expectation formula. So if you see the solution, this is the solution. So for the ground state in hydrogen atom, psi 100 is the ground state. So it is 1 by this. Okay, like this. And if you apply the expectation value, that is bra psi r ket psi. Okay, so if you use this and you do the calculation and you apply the gamma function rule here, especially here, okay, then you will get the value of expectation value of a hydrogen atom like 3 a naught by 2. Okay, so now coming to the 53 number question, it is given that the radial part of the wave function in the ground state of hydrogen atom varies as. How it is varying, the radial part in the ground state? So we have come across about the wave function, that is it looks like this. This is the ground state wave function. This is partial visible. You see this is the ground state wave function for the hydrogen atom. Okay, now if you see that here psi 11, if you see the actual solution, if you see here psi 100, that is 100 is this. Okay, this is the ground state wave function. Here we can write this psi 100 as r10, that is the radial part, and y00, that means L and M in the harmonic part. This is y00 is the harmonic part, and here L is 0, that means M is 0, the corresponding quantum number, angular quantum number, or you can say azimuthal quantum number. Okay, so it is 0. So when it is 0, that means we are asked to find this radial wave function. Okay, and we know that this y00 part is nothing but this term, this term. This is it is given like this. Okay, so definitely that means R10 is this much. Okay, so it's varying like this. So this option is correct. Okay, so now coming to the 54 number question. For Pauli spin matrix sigma, and for Pauli there are three different Pauli matrices: sigma x, sigma y, and sigma z. Choose the wrong statement. The first statement is given like this: sigma x and sigma y commutes, and the first option is itself a wrong statement. Because why? Because these two sigma x and sigma y don't commute with each other. Okay, so actually they do not commute. If you see the solution, sigma x is this, sigma y is this, sigma z is this, and if you try to find the commutation sigma x and sigma y, it is like this. Okay, you go through the conventional method, and you ultimately find that it is equal to this. It's equal to this much. Okay, it is equal to this. So as it is not 0, 2I sigma z, it is not a 0. So if this quantity, if this quantity is equal to 0, that means it is commuting. But as it is not 0, that means it is not commuting. So that's the thing. Okay. So option A is the wrong statement. Okay. So option A is correct. Now coming to the 55 number question, it is asked to find the Clebsch-Gordon coefficient for this. Clebsch-Gordon coefficient for this term. Okay, that is two bases are multiplied here. That is we have to find the inner product or the scalar product of these two bases. Okay, and what is this Clebsch-Gordon coefficient? It is nothing but when you transfer one basis to another basis system, the intermediate part, that is the coefficient that you multiply with the another basis, and with that multiplication we get the another, we get a new basis. That multiplication constant is the Clebsch-Gordon coefficient. Okay, and it's nothing but a matrix. Okay, it's nothing but a matrix. And if you see the solution, this is the matrix, and here this is the Clebsch-Gordon coefficient matrix. Okay, this is the Clebsch-Gordon coefficient matrix, and here in this part, this is a one kind of basis system, and we are trying to transfer this basis into another basis system, that is in this basis system. Okay, so actually my argument is that you look only this part, that is only this part. This is our main thing. Okay, so if you multiply what it is given to find, if you see the question again, it is asked to find this quantity. Okay, so now you see where this term can be calculated. You see, if you multiply this basis with this one, I think, let me see, minus 1 by 2, 1 by 2. Okay, minus 1 by 2. Okay, this quantity, if you multiply this with this, then the corresponding coefficient is what? Minus 1 by 2. You will get minus 1 by root 2. Okay,